compared to 2 years ago, we really upgraded, at least for the room, but also I think the number of people are much more. So, deep learning for molecular kinetics. Before going into that, I wanted to kind of give a little update on where I think we are with Markov state modeling in general, because this meeting is mostly Markov state modeling. And thanks to the fact that this is the second day, I don't have to go too much into the basics. So, as you know, we can do molecular dynamics with a high throughput by either having a dedicated supercomputer, or if we don't do that, by basically buying many GPUs that will still give us a very good throughput if we have like hundreds of them. But this data will come in the form of many short trajectories, and then we need to figure out what we do with that, especially how do we compute expectation values like affinities, rates, etc. And so the basic idea is we can sample the rare events by sampling many not so rare events and putting them together and hoping that none of these individual barriers are too high so that we can't sample across them. And one of the main tools we're using, or many people in this room are using, is Markov state models. So Markov state models, of course, in principle, a very old concept, but in the field of molecular dynamics, essentially this goes back to Christoph Schütte, who thought about this in the late 90s and wrote down some mathematical ideas how to address the molecular dynamic sampling problem with short trajectories and Markov state models. And then in the mid-2000s, several people, starting with a small group, I remember meeting John on a conference. Actually, I met Ken Dill on a conference, and he brought us all to San Francisco. And then John, Bill Swope, Nina Singal, and I met, and we talked about these things and started working in this field. Initially on mostly peptide dynamics, small protein folding, reconstructing, folding pathways for proteins, etc. Because that's what we could do at the time. And then later, computers got more powerful, we got more throughput, methods got better. We could do things like ligand binding, ligand unbinding. This is a work on trypsin benzamidine that basically studies different conformations of the trypsin protein as it binds to benzamidine. And interestingly, these different conformations can be related to the ground states, so the X-ray structures of other serine proteases, which is the protein family that trypsin is in. So these are the kinds of things that MD and Markov state models combined are good at, like understanding what relevant states do we have in a protein, what are mechanisms of switching between these states, and what are binding rates, unbinding rates to and from these states. Although unbinding rates, that's a bit tricky because unbinding rates involve rare events, and they may involve some steps that are very rare. So here's some work in collaboration with Johnny, where we looked at protein-protein association. And so we, after we've seen that we could essentially bind ligands to proteins spontaneously and find the binding pocket, we thought, okay, let's just put two proteins in a simulation box and essentially just run a lot of MD and see if we can get that too. And so the system that I want to talk about here is RNase FASTA. Very simple protein-protein system, small proteins also. But with the explicit solvent, this is still already about 100,000 particles. And the problem here is RNase FASTA is really a tight complex. So it's about 18 kilocalories per mole is the free binding energy. So the dissociation rate for this guy in equilibrium is about 1 hour. So, and that seems to be a problem for all atom MD. Okay, but so following some ideas from active learning and in the field of Markov state modeling, this is actually called adaptive sampling, and Greg has worked a lot on this. We said maybe we can use Markov state models in combination with MD trajectories to speed up the process. So we basically run parallel copies of unbiased and molecular dynamics. Every now and then collect the data, build the model, and decide in some way which of these conformations are more promising to launch new trajectories And in this case, the idea was basically, let us explore the slow subspace. So let us find the slow coordinates, the coordinates that best describe the rare events that we have seen in the data so far, and essentially try to cover this subspace efficiently. There's actually some very nice work of Cecilia 3 years ago where she used diffusion maps to do that, and this is using Markov state models. And this way we basically try to explore the space of slow coordinates faster. And so it turns out that with an aggregate simulation time of a few microseconds, up to a few tens of microseconds maybe, we can reliably bind the proteins to their native structure if we just start from dissociated states. But also we can, within an aggregate sampling time of about 100 microseconds, dissociate the proteins from their native complex, which is, of course, much faster than it should happen in equilibrium. So either our force field is completely wrong, or we had some acceleration here. Okay, so this way we collected basically lots of binding and unbinding and association-dissociation events and built a Markov model, a hidden Markov model in this case. So first of all, we can compute some quantities like the binding energy, the association rate. Association rate is very good. Binding energy is within the statistical error around the experimental value. This is a mutant, so it has slightly lower binding energy than the 18 kcal I cited earlier. But of course, the uncertainty here is really large. 2.5 kcal per mole, if you translate that to a rate, is a huge difference. Right? But I'll come to that. What else do we get? We find that the most stable, metastable state, most stable Markov state corresponds to the crystal structure. So this is the actual crystal structure drawn in the in a density of the simulated metastable state. So that seems to fit really, really well. And we also did some free energy perturbation calculations to compute the changes in binding energy and the changes in binding rate if you do alanine mutations, and that could be compared to experimental data. So what we get is we basically get a network describing the binding of these two proteins from the dissociated state over some early intermediates where they are in contact but not in the right conformation, to a bar star being in the binding pocket of Barnase but having the wrong orientation, to eventually a stable complex. And this stable complex actually seems to consist of two substates, which is a new insight, or at least this proposed state hasn't been reported before. But before coming to that, I can basically just visualize the trajectory. So this is a visualization of a binding trajectory which has been sampled from the Markov state model, and then we go back to the database and essentially concatenate trajectories to produce this movie. So this is 100 microseconds that we have never simulated as such, but it gives you an idea of how binding proceeds. The proteins search each other's surface, then they might just dissociate and later come back. But if they stay in contact, eventually they will find the docking pose and bind tightly, and then stay there for a very long time. And then we can analyze the native substates that we found. So this extra state we found, for example, that's more loosely bound state. Roughly speaking, it consists of this bar star protein being slightly rotated from your point of view to the right with respect to the native binding pose. And one hallmark of it is that this tryptophan residue is exposed, solvent exposed, so that should have a different spectroscopic fingerprint than the native state, and this being in the microseconds to hundreds of microseconds time scale should make it accessible to, let's say, tryptophan fluorescence correlation spectroscopy. Okay, but so, I mean, the cool thing, or the methodologically cool thing about this work is that you do get dissociation events throughout this network that are consistent with a dissociation time of 1 hour. The problem is it still has very large uncertainties, so you wouldn't want to use this as an effective tool to compute this number if the number is the thing you are after. So what can we do about this? So there are two things that at least we need to address, but I'm not going to address them in my talk because they will be addressed in other talks. I have already been addressed in other talks. So just a pointer. So a much more efficient way to compute binding and unbinding kinetics for these very rare events is to use enhanced sampling simulations in addition to your unbiased simulations. And those can be combined with a framework called multi-ensemble Markov model, which is basically a reweighting framework, which combines all of these data and in contrast to classical reweighting methods that only reweight the stationary distribution, you also get the kinetics of the system, at least if you have an unbiased ensemble in your different ensembles. So this is something that Fabian will talk about today. So I'm not going to talk about that anymore. So with this you can get high precision, so small error bars for the binding rates. But then they're typically still off with respect to the experimental value because we're using a force field. So one way of solving this is to work on force fields. Maybe solving this is to work on force fields, at least improving it. It's probably hard to solve it altogether with better force fields because every force field has a limited range of applicability. But one thing we can do is we can, instead of just blindly predicting something with an MD simulation and a Markov model and then hoping it is kind of consistent with experimental data, we can include experimental data when we have it in the process of estimating the model. So you add this information to your estimation procedure. And this is something that Simon talked about yesterday. So augmented Markov models, so that's a way to add experimental data into these simulations. All right. So now I want to come to some new developments that involve deep learning. And so deep learning is a technique that is good at a couple of things. And one of them is to find good nonlinear feature transformations. So Markov state modeling is one problem where finding a good feature transformation is essentially the core of the problem. So we have this software, PyEmma, that we're distributing that many people are using now to build Markov state models. And like 95% of the comments and problems that we see that people have when using the software are very early in the process. Like how do I load my data, how do I featureize my data, how do I project it on some lower dimensional space, etc. So this whole procedure of building Markov state models, even though this field is not that young anymore, we have a conference here on that topic. There are hundreds of papers, there's a lot of knowledge, there is pretty good software out there, MSM Builder and PyEmma that really do a lot of the hard work. It's very hard to use this technique because there are so many steps where one could get something wrong, right? So there's the feature transformation, the clustering, then the estimation, etc. So if you don't have like a lot of domain knowledge, it's very hard to get everything right, and getting one step wrong is enough to get a bad model. So we thought maybe we can just replace all of that with a deep network, right? All of these steps. And the idea goes back to the fact that there is a way to describe this molecular dynamics Markov modeling problem in a so-called spectral framework. So Markov state models are theoretically built on the idea that there is a dynamical propagator which describes the dynamical evolution of your MD system. And this propagator has eigenvalues and eigenfunctions. And like in quantum mechanics, where you're looking for eigenstates, the problem of Markov modeling or building a similar sort of kinetic model is a problem of approximating the eigenvalues and the eigenfunctions of this guy. The problem is just you don't have this operator in any practically useful form. You cannot actually compute integrals over it like you can do in quantum mechanics if you have a suitable Ansatz function. But that is an important piece of theory, which basically tells us what are the things we need to go after to get a good model. And the formalization of this approach is this variational approach, which basically says this, like in quantum mechanics, where you have this Rayleigh variational approach, you have variational approach here, where you basically compute expectation values from your data, and you're trying to maximize a certain score, a certain number. This number tells you what are the autocorrelations at a certain lag time along the directions that your Markov model picks out as the slow directions. And having this principle, we can now use it to teach a neural network to learn what is a good model. So we just essentially write down this principle in a computable form and train a neural network with it. Okay, before coming to the neural network, so the method that is based on this principle, or that can be explained based on this principle, let's say, is the TICA method that probably many of you know, which is a linear method that uses this principle. Linear method means you select some candidates for functions of coordinates, for features, and you look for a combination of them. Like we do that in principal compound analysis. In TICA, you look for a combination of them that makes the coordinates to point to slow directions, slow reaction coordinates that are good for Markov state modeling. And these neural networks that use the variational principle have the same idea behind them. So we call them VAMP nets because they are based on the variational approach for Markov processes, VAMP. And what they basically do is they take the input configurations, actually the time-lagged input configurations. So this is just essentially a frame of your MD data, and this is the frame tau time steps later. And they feed this data through a multi-layer neural network that could be built in different ways. In this work, we've just used normal dense networks with rectified linear unit activation functions, so that's something very simple. But the fact that you have many of these layers and each of them have some nonlinearities in them makes the overall mapping a nonlinear mapping. So this is just a nonlinear function which maps a MD configuration xt to this chi0. And because we want to learn a Markov model, we decide to design these chi's to be assignment functions. So these functions here will have what's called partition of unity property. So basically, they will assign every configuration x to one out of n or metastable states. So the number of output neurons we have here is just a number of metastable states we want to have in the model. And this vector here sums up to 1 over the output layer. So it probabilistically assigns our configuration to any one or multiple metastable states, multiple if you're somewhere in between on a transition state or something like this. So this defines a feature mapping, but it directly defines a feature mapping to a coarse-grained metastable states assignment. So all we need to do at this point, if this is good, all we need to do is to essentially compute a matrix which tells us what is the transition probability in going from here to here in time tau. So that's a very simple Markov state model, because all the work of featurization, clustering, coarse graining, blah, 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 has already been done. And then we just train the whole thing with this simple score here, which basically involves covariance matrices that we can just compute from the data in batches. And then we can use normal machine learning techniques like frameworks like TensorFlow or PyTorch or whatever to maximize this. And so you're learning everything together, feature transformation, the clustering, the coarse graining, everything. You're not making decisions at every step. This is all somehow hidden in the network. Okay, and you can do the usual things with this network that you're doing with Markov state models. So you can compute the transition metrics, you can compute the timescales, you can test the Chapman-Kolmogorov tests, etc. So, few examples in this double well problem. If we do this with 5 states, we find a state in the left and in the right well, and we find several states discretizing the transition state. And this is actually needed if you want to get a good Markov model. So you need several states to discretize the transition state. And if you compute the implied timescales, you see they're basically completely flat. And the Chapman-Kolmogorov tests show a perfect overlap between the predicted relaxation curves from an initial distribution to the stationary distribution in these states with the data. So you get very high accurate Markov state models. Same for allylinear peptide. You get, in this case, a model with 6 states for these 6 long-lived states here, corresponding to free energy minima on the psi plane, and also a very good Chapman-Kolmogorov test. So you get very high accurate Markov models. Okay, this is just for different numbers of states. So then the size of your output layer controls how many states you get. 2, 3, 8, etc. You can choose this number by maximizing the score that we are maximizing, not for the training data, but for the validation data, so for a held-out data set, because it's a hyperparameter. And so the interesting thing here is that the Markov model somehow learns what smart features are implicitly. It's very hard, sorry, the network learns that. It's a bit hard to ask the network, what did you learn? This is actually a big topic in the field of deep learning, to design better techniques to query networks and to find out what is actually, how can I interpret the many weights that are somehow in the network? What do they mean in practice? But so one thing that we could easily do is, in allylinear peptide, we know there are 2 important variables, phi and psi, the hedral angles. So we just learned a VampNet which was forced to go through 2 nodes as a bottleneck. And then we asked, are these 2 nodes, are the activations of these 2 nodes in any way related to phi and psi? So the input is Cartesian coordinate, so the network doesn't know anything about torsions. And you need to get a very high correlation with phi and psi. And the network learns to partition the phi psi plot pretty well. These 2 states are always a problem because this state has very, very little population, so it's hard to get it right. So these get mixed up, but the others are well separated. Okay, and this is in principle, of course, applicable to large systems. So this is not yet a large system, but it's an intermediate system. This is an NTL9 folding trajectory from the D. Shaw Anton data set. And building VampNets with different numbers of states resolves folded and unfolded for 2 states. And for 5 states, you resolve different folded and different unfolded or intermediate substates. Okay. And so now the more recent things that we are interested in involve generative machine learning. So one of the big limitations, I think, of all of this MD and Markov state model business is that you invest a gigantic amount of work in producing simulations, and then you build a model, and then you have one model for that one system that you have simulated. And now if you want to change something, like with the experimentalists ask you, what should I mutate? How can I test these hypotheses? Then you can basically look at things and hopefully have a chemical intuition, which I don't because I'm not a chemist. So I would prefer to have like a computational method that efficiently tells me what happens if I change something. So essentially, we don't just want to go from configurations to variables that describe the model in some reduced space, but we also want to be able to go back. And this is called generative machine learning. And just to give you one example of a generative machine learning technique that is frequently used, this is a generative adversarial network. An adversarial network uses the following idea. It has 2 networks that compete each other. So you have one network which has noise as an input, so random variables, and it maps these random variables into a new space, into a space where your structures live that you want to generate, for example, molecular structures or chemical structures or images or whatever. So this is a complex, this generates hopefully complex variables or vectors from simple to sample distributions. So it has to learn how to do that, how to transform this random vector in a somehow weird, complex, nonlinear way to get a meaningful structure out. It needs to be trained to do that. And one way to train is to learn another network called the discriminator, which is shown either real samples or these fake samples that have been generated artificially. And the discriminator gets a reward when it successfully tells whether this is a real or a fake sample, and the generator gets a reward when it fakes the discriminator. And this way these networks play against each other, and if they converge, which is not easy, you can get good samples out of your generator. And you can do cool things with this stuff. So in this space here, that is basically the input space of the generator. This is now called the latent space. This is some sort of embedding of the images or molecular structures in which somehow the metric is meaningful. The distances are somehow meaningful, hopefully. Like similar things in some sense will be close to each other. So you can do arithmetics in this space. That's one of the nice side effects. So you can do things like this. These are images, generated images actually, of guys with classes. These are images of guys without classes. These are images of women without classes. And you take a guy with classes, subtract a guy without classes, add a woman without classes, and you get a woman with classes. And this is, of course, completely meaningless in pixel space. You couldn't do this in the original space. So the aim is to get like a low-dimensional representation of the data in which you can do simple operations like this. Or do mutations, if we're talking about molecular structures. Okay, so I'm essentially out of time, but in one minute I can do this. So we've not used this exact structure, but another machine learning structure for generative networks. And this is very recent work. Actually, I just submitted this this morning, so this will be coming out soon on the archive. On a deep generative Markov state model. So now that's a Markov state model, which hopefully has all the benefits from the previous VAMP nets. So getting a really good high accuracy model, finding a good feature transformation that allows you to get a good Markov state model. But also we want to be able to map back from the space of metastable states to structures. And there's a little trick we can do here. We can take this generator and plug it back into here, into this encoder. And then basically the mapping from here to here defines a transition matrix. And with this little trick, we can build everything such that we get a truly probabilistic model. So we get a real transition matrix with non-negative numbers in it, so actual probabilities, that is probability conserving. And so everything is probabilistic. We could embed this in a Bayesian framework, for example, which is very nice for computing errors, etc. And so, again, training this just on alanine dipeptide shows that, well, this is just the data distribution. This is a good classical MSM. This is such a deep Markov state model, which doesn't have a real generator, but which just essentially resamples the data from the distribution it has learned. So this is just basically a fancy MSM. But this last guy here actually learns an output distribution. And this output distribution is in Cartesian coordinates, not in 5-psi coordinates. I'm just showing 5-psi projections here. So it gets, at least approximately, this distribution right. It gets too much population in these undersampled states, but more or less it gets these states right. And now if you look at the structures, they look pretty good too. But now I do an additional experiment. I leave out data from the training set, and I ask if I remove data from the training set on purpose, if I never show the network what this state here looks like, can it still generate one for me? Right? So can it sample genuinely new structures that are meaningful, so that are somehow not physically complete garbage, like all the atoms in one point or something like that? And could be, for example, used for further sampling or whatever. And that seems to work, at least in these 4 cases. It doesn't work in these two low populated states where you see that the structure and the density here are not overlapping well. So the structure is a real MD sample, and the cloud of lines is generated structures. But we have a lot of problems with these two states anyway. But these four states here look pretty good. So we trained it without knowing that this state exists. The network proposes samples in this state. Quantitatively, the density is wrong. It doesn't know that there should be a metastable state. But it proposes structures there that look right. And if you look at internal coordinates like bond lengths, angles or so, they're pretty good too. Yeah, not perfect, but with a bit of refinement, MD, optimization, whatever, you could get that right. So, okay, I should finish. I want to make a short plug to an IBM Long Program in fall 2019 that Cecilia and I and several others are organizing on the physics of machine learning and using machine learning for physics. And with that, I would like to thank the people in my group that produced this work, and the funding agencies, and you for your attention. And I already went over time, sorry.
You also saw that, so I could see how far. I think we still should have some time for a couple of questions.
Just curious with adversarial networks, it sounds really nice to be able to propose mutations. It basically needs to learn which force fields or something, right?
Yeah. Essentially, yes. That's the idea.
I mean, is it working, or is it a nascent idea?
So that's, I'm not aware of how that can essentially generate structures in one shot. So the tricky part with these networks, which is also the nice part if it works, is that they are essentially one-shot methods. So you put a random vector in, you get a structure out. And I think that's a very hard problem. I think it's probably easier if you can go through iterations and essentially learn some sort of smart Monte Carlo steps. So we are trying to go in that direction also. If you additionally have additional information about what is reasonable, like a simple energy function or so, that at least tells you if you're producing clashes or so, to use that to essentially train smart steps. I think that's, for really complex structures like proteins, that's more likely to work.
About using ramp as a scoring function for the networks. So ramp's like a global metric that's trained traditionally on entire data, but you use it as a local score for batches of data that go through the network, one at a time.
Yes.
How would you expect them to be the same in some ways?
You have to sample from the same distribution. So that's, I mean, the principle of these mini-batch methods is basically you have an underlying distribution from which the data comes. And the idea is that whenever you compute a score or a gradient, then essentially this has the form of an expectation value. So subsample this expectation value.
But wouldn't that mean that every batch needs to sample the slowest possible?
It needs to have they need to have the same chance of sampling it. It doesn't mean that every mini batch has to sample the slow process, because you're only doing small iterations in your parameters. So if you have like 1,000 mini batches which don't contain the slow process, then you will go 1,000 times a step into a direction which doesn't contain that process. But then you're sampling a mini batch which contains this process, and you'll go a direction in that step. I mean, statistically, if you're sampling from the same distribution, so if the covariance matrices that you're computing at every batch actually sample data from the same distribution, like the entire thing, this should work. It is a good question. If can we maybe do better by somehow presenting the data to the network with a different distribution, by not sampling from the same underlying distribution?
I was thinking more like any mini batch, let's say 100 nanoseconds, you can sample the rate of process once. Expected time schedule within one. And might be a process which is what needs to in every 100 nanoseconds process will add noise to the gradients at every time. So maybe it doesn't matter if you have
So, yeah, all I can say is that from a theoretical standpoint, these mini-batch methods should work if the distribution is the same. But there could be pathological situations in this rare event scenario, and this is not a thing that is very well understood in machine learning. So often the assumption for these methods is that data are stationary, and the distributions are kind of like fair, or like different classes are sampled uniformly. And we are in a situation where we're very far from that, and I think there's not a lot of understanding in the field of how these methods deal with that. So it's an absolutely fair question, but that's all I can say so far.
Last question?
You mentioned
Just to show that we can find the bound state. We can unbind it. Yep. Yep. So this was probably a bit too fast. This plot here shows you the root mean square distance to the native complex. So we start large and we converge to a small number around 2 angstroms. That means we find the native complex. And this is like the minimum over all the simulations that we have done thus far. So it just decreases. And here we start from the native complex, and in this trajectory, or in this simulation, in 100 microseconds total, we dissociate. So this is just to show that you can truly associate and dissociate for this problem.
Those are nanometer units, is that right?
Yes.
You said angstroms, like nanometer.
Yeah, sorry for that. Yeah, that was stupid. Yeah. Thanks for pointing that out.
Thank you very much.